All right, so you've heard all about large language models, right? They're kind of like the brains of this whole AI revolution. But what about their memory? Well, that's where vector databases come in. Today, we're diving into the tech that gives AI a long-term memory, letting it not just spit out answers, but to actually remember, understand context, and, well, to understand.
So here's what we've got on tap. We're going to start with the absolute basics. What even are vector databases? Then we'll get into the magic of indexing that makes them so fast. We'll see how they power modern AI with a cool trick called RAG, take a quick peek at the major players in the game, and then we'll look to the future. What's next for smarter AI agents? Let's get into it.
Okay, first things first, what is a vector database? To really get it, you've got to think about how old school databases work. They're fantastic at finding an exact word or a number you're looking for, but they're kind of clueless when it comes to something we humans do effortlessly, understanding meaning.
And this example just hits the nail on the head. Imagine searching a traditional database for the word war. You'll get every document with that exact word. But what if what you really want is something about the philosophy of conflict? Modern AI needs to be smart enough to connect that phrase to, say, the art of war. Even if the word war isn't in your query, it's about concepts, not just keywords.
So that's the big question, isn't it? How on earth do you get a computer to search for meaning instead of just matching letters on a screen? How do you teach it nuance? Well, the answer, as it often is with computers, comes down to one thing: translating our messy human world into the clean, crisp language of math.
And the solution has a name: vector embedding.
It sounds complicated, but the idea is actually pretty cool.
An AI model takes a piece of data, could be text, an image, whatever, and turns it into a list of numbers. We call that a vector. But here's the magic trick. It's not just a random jumble of numbers. The model cleverly arranges these vectors so that similar ideas, similar concepts, are placed close to each other in this giant invisible map of meaning.
Think about it like this. You're shopping online, right? You look at a pair of jeans. The website doesn't just show you that exact pair over and over. It gets the vibe. It knows the style, the cut, the brand, and it starts recommending similar stuff even from totally different brands. It's finding things that are close by in style space. And that's exactly what a vector database does, but with all kinds of data. Okay, so we've got this incredible map of meaning. But now what? How do you actually search it? I mean, we could be talking about billions, with a B, of these vectors. Going through them one by one to find a match? No way. That would take forever. This is where things get really, really clever. The big idea is this: you don't actually need the single best match. You just need something that's really, really close. This is a technique called approximate nearest neighbor search, or ANN for short. And it's a brilliant trade-off. You give up a tiny, tiny slice of perfect accuracy, and in return, you get a mind-blowing boost in speed. It's what makes searching these massive data sets feel instantaneous. And there are a couple of popular ways to do this. You've got IVF, which is kind of like organizing a library. You group similar things into buckets or sections. When you search, you just check a few of the most likely sections. It's super fast, but you might miss the perfect book if it's sitting in the next style over. Then there's HNSW. This one is more like a social network, or a 6 degrees of Kevin Bacon for your data. It creates all these connections between similar points, so a search can quickly hop from one point to another to find the right neighborhood. It's generally more accurate, but can use a bit more horsepower. How you build this indexing system is a huge deal. As Pinecone points out here, you can't just staple a vector search feature onto an old database and call it a day. Those bolted-on solutions, they just can't keep up. Real-world AI needs something built from the ground up for this stuff, which is why these dedicated, purpose-built vector databases are taking off. All right, so this brings us to the absolute killer app for vector databases right now. It's called Retrieval Augmented Generation, or RAG. You're going to hear that acronym a lot. Basically, RAG is the secret sauce that lets large language models tap into knowledge that's way outside of what they were originally trained on. And this really breaks it down perfectly. Think of an LLM's context window as its short-term memory. It's like the stuff you can hold in your head right now, but it's limited and it forgets things pretty quickly. The vector database, that's the long-term memory. It's practically infinite and it's perfectly organized. It's an external brain the LLM can consult anytime it needs a fact. So how does this RAG thing actually work? Well, it's a pretty elegant workflow. You ask a question. Step 1, your question gets turned into a vector. Step 2, that vector zips over to the database to find the most similar, most relevant chunks of information. Step 3, that new info, that context, gets tacked onto your original question. And finally, that whole bundle gets sent to the LLM. The result? You get an answer that's not just pulled from some old training data, but is grounded in up-to-date, relevant facts. Okay, so we get the tech now. It's powerful stuff. But who's actually building it? Well, this whole field has just exploded, creating this really exciting landscape of companies all trying to crack the code, and they all have their own unique spin on things. And here's a quick look at the major players. You've got your managed services, like Pinecone. They're all about making it super simple to get up and running. Then you have this amazing world of open source options. Weaviate, Chroma, Qdrant, Milvus, giving developers tons of flexibility and control. And of course, you can't forget the big established players like Elastic, who are now adding top-notch vector search right alongside their world-class keyword search.
And believe me, this market is on fire. We're talking about $1.8 billion in 2023. But look ahead to 2033, the projection is over $13 billion. That's a growth rate of more than 22% every single year. Why? Because literally every industry is scrambling to integrate AI. And this is the memory they all need.
So, what's the end game here? Where does this all lead? Well, if you give an AI a perfect memory, the next logical question is, what can it do with that memory? And that, my friends, is where we start talking about the next huge leap in AI, autonomous agents. And you can already see the building blocks falling into place. Things like hybrid search, which gives you the best of both worlds, the precision of keywords, and the context of vectors. You've got multi-tenancy, which is a fancy way of saying it's getting way cheaper and easier for companies to roll out AI features. And of course, GPU acceleration is just making everything faster and faster. We're talking real time. And really, this is the key thing to remember. A persistent, searchable memory. It isn't just some cool feature. It is the absolute foundation for building AI that can do things, not just chat, but perceive, remember, plan, and actually act on its own. This is what lets an AI learn from what it did yesterday to plan what it's going to do tomorrow. So, think about how far we've come. We've moved from just searching for words to searching for actual meaning. We've effectively given AI a nearly perfect memory. So, the big, thought-provoking question is, now that it can remember anything and everything, what are we going to ask it to do next?